Doing this always reminds me of my childhood. I'm sure you have been scolded for doing this too. But you know, even the gases in these balloons are like naughty children. Want to know about the pranks they play? Keep thinking.
You know, it is impossible for you to behave obediently, and ideally for all times. Gases are no different. So let's begin our discussion by defining an ideal gas. An ideal gas is defined as one in which all collisions between atoms and molecules are perfectly elastic and in which there are no intermolecular attractive forces. But there are other conditions under which even gases deviate from ideal behavior. What are these conditions? Let's try and understand.
In today's episode, we will look at deviation from ideal behavior, liquefaction of gases, critical temperature, all you need to know on how to crack those exams in the exam decoded section.
We know for exactly 1 mole of an ideal gas, PV divided by RT is equal to 1. A plot of experimentally determined values of pressure times volume divided by the product of gas constant and temperature for 1 mole of different real gases as a function of pressure is shown in the graph. Notice that the graph shows a deviation from the ideal value of 1. Let us define PV over nRT as Z and call it as the compressibility factor, which should be unity for an ideal gas, as you all know. The deviation from ideal behavior is large at high pressure and low temperatures. Isn't this much like us humans? We also deviate from ideal behavior with increasing peer pressure and with less parental intervention. Just like we behave differently in different circumstances, the ideal gas equation doesn't work perfectly for all gases under all conditions, simply because it is based on imperfect assumptions such as
the volume of the molecules
is not comparable to volume of space. Particle interaction should be elastic. The two assumptions are wrong for all gases. At high pressures and at low temperature, the intermolecular distance in gases become quite short, which is why the attractive forces between molecules become significant. At this point, it becomes important to understand why real pressure deviates from ideal pressure.
Increase in pressure lead to an increase in intermolecular attractions. Increase in intermolecular interactions lead to a decrease with which the molecules collide with the walls of the container, that is, it decreases the pressure. Thus, the measured pressure or real pressure is less than the calculated pressure from the ideal gas equation.
In order to use the observed pressure, that is the real pressure, in the ideal gas expression, we must correct the decrease in pressure due to molecular interactions. Thus, the reduction in pressure due to molecular interaction should be proportional to n over v whole square. If the proportionality constant is called A, then the ideal pressure is equal to real pressure plus A times n square by V square. Thus, correcting for molecular interactions alone, the ideal gas equation would become P plus A times n square over V square. The whole thing multiplied by V, which is equal to nRT.
As pressure increases and temperature decreases, the volume of the molecules becomes significant as compared to the volume of the gas.
To correct for the volume, we must recognize that in the ideal gas equation, the volume used is just the gas volume minus the volume that is taken up by the molecules of the gas itself. Thus, ideal volume is equal to real volume minus N times B. Thus, the ideal gas equation, if corrected for molecular size and interactions, looks like
P plus A times N squared divided by V squared times the whole of V minus NB is equal to nRT. This equation is called van der Waals equation, and the constants A and B are the van der Waals constants.
Now let us study the compressibility factor of a gas, taking methane as an example. There are quite a few important points to keep in mind, so pay close attention. The compressibility factor Z is defined as the ratio of pressure times volume divided by the product of number of moles N times the gas constant R times the temperature T. Since product of pressure and volume PV is equal to the product of the number of moles N times the gas constant R times temperature T, that is nRT, for an ideal gas, then Z, the compressibility factor, is equal to 1 for an ideal gas. The compressibility factor Z varies with pressure or temperature for all gases. For methane, Z can be high and as low as 0.6, showing considerable deviation from ideal gas behavior, particularly at low temperatures and high pressures. As the pressure becomes lower and the temperature becomes higher, or if both happen simultaneously, the gas becomes more ideal in terms of its physical behavior and particularly ideal as the pressure tends towards zero.
Values of Z for a non-ideal gas.
For a gas with Z greater than 1, the molecules occupy more volume than the volume of the ideal gas. These gas molecules have repulsive forces. An example of such a gas would be hydrogen, H2. For a gas with Z less than 1, the molecules occupy less volume than ideal gas. The molecules of such a gas would be having high attractive forces. An example of such a gas would be carbon dioxide. The temperature at which a real gas behaves like an ideal gas over an appreciable range of pressure is known as the Waals temperature. Quite a lot to remember, isn't it? Let's take a break, because on the coming half we are going to discuss critical behavior in gases and critical point. Meanwhile, here is a question for you. Van der Waals equation explains the behavior of what kind of gases? Keep thinking. It has been often said by many great thinkers, within the question lies the answer. We have been discussing gases and their behavior. Before we went to a break, I asked, Van der Waals equation explains the behavior of what kind of gases? Well, the answer is as simple as it can get. This equation is used to explain the behavior of real gases. The constant B is related to the effective volume of the gaseous molecules. Van der Waals constant A is related to the ease of liquefaction of the gas. Now it's time to take a look at the critical behavior of gases. Cooling of a gas slows down the motion of the gas molecules, so they take up less space. Similarly, pressurizing a gas or forcibly squeezing its molecule closer together reduces its volume. In time, through cooling and compression, the volume of a gas can be reduced by so much that the molecules collapsed upon each other and come to contact, changing into a liquid. As P is increased at constant T, at some point liquid will form. The liquefaction occurs at constant P, the horizontal line on PV plot. The critical temperature, Tc, of a material is the temperature above which distinct liquid and gas phase do not exist. Above the critical temperature, a liquid cannot be formed by an increase in pressure. The critical pressure is the pressure at the critical temperature. The critical volume is the volume of 1 mole of gas at the critical temperature and pressure. No study is complete without a revision. So, let's do a quick discussion of the topics we covered today. We discussed, number 1, deviation from ideal behavior. Number 2, liquefaction of gases. Number 3, critical temperature. I bet we are all prepared for a round of questions. So, without further delay, here is the first one, which was posted on our website www.topperlearning.com. Out of nitrogen and ammonia, which one will have a higher value of A and B? That's easy. A depends upon intermolecular interactions, which are more in ammonia. Therefore, ammonia will have a higher value of A. The value of B depends on molecular sizes. Larger the size, greater the value of B. Therefore, nitrogen will have a higher value of B. Another one coming up. Is it true that a gas can be liquefied by pressure alone when its temperature is higher than critical temperature? Let's see how some of your peers from different schools have answered this.
Is it true that the gas can be liquefied by pressure when its temperature is more than its critical temperature?
It's definitely false.
Yes, it's true that gas can be liquefied by pressure alone.
Well, that's 2 against 1. The answer is false. A gas cannot be liquefied by pressure alone when its temperature is higher than critical temperature. We have another query from a student. Let's try and answer this one together.
Why do gases deviate from ideal behavior at low temperature and high pressure?
That was a good question. The answer to the question is, the ideal behavior of a gas depends on the following important assumptions. The first one being,
The volume of the molecules
is not comparable to the volume of space. Secondly, the particle interaction should be elastic. That is, there are no attractive forces between the particles. At low temperatures and high pressures, these assumptions are violated and gases show deviation from ideal behavior. The influence of intermolecular forces are stronger and
the actual molecular volume becomes important.
Hope the answer is clear in your mind now. I'm just about ready for a break. and I bet so are you. So let's take one. Here is one question in the meantime. What is the significance of van der Waals constants? Keep thinking. I hope you have cracked the answer to the question I had asked you. What is the significance of van der Waals constants? Van der Waals constant A is related to the ease of liquefaction of the gas. Greater the value of A, the greater are the forces of interaction and the easier it is to liquefy the gas. The constant B is effective volume of the gaseous molecules. Larger the value of B, larger the molecular volume. Now, let's prepare you for exams. We have a range of questions and tips for you to score an edge. Let's start with some probable questions from the topics we studied today. The first question for 2 marks is, why is critical temperature of carbon dioxide higher than that of hydrogen? Another question for 2 marks only is, why is compressibility factor of hydrogen and helium greater than 1? The third question, what happens in case of inelastic molecular interaction of gases? This will fetch you 2 marks. For 1 mark, tell me what is the difference between a vapor and a gas? Answer the next one for 2 marks. What would happen if the value of A would become equal to 0? The last one for 3 marks is, with an example, explain how the values of van der Waals parameters vary from gases to gases. Ever wondered how to write an answer to score full marks? Watch closely as I show you how to write an ideal answer. If you get a question like, why is critical temperature of carbon dioxide 304.15 degree Kelvin is higher than that of hydrogen 33.2 Kelvin? For 2 marks, here are the facts that you need to state. For hydrogen gas, the forces of interaction between gaseous molecules are very less and therefore its critical temperature is 33.2 Kelvin. For carbon dioxide, on the other hand, the intermolecular interactions are high, which is the reason why critical temperature is 304.15 Kelvin. For a roundup, we have an expert who will list the important points from today's topics. Follow them closely. You can be assured of acing your exams.
The first one, you must remember the conditions for an ideal gas. Deviations from ideal behavior occur only under low temperature and high pressure conditions. The third one, the compressibility factor Z is equal to 1 for ideal gases. Easily liquefiable gases like carbon dioxide, sulfur dioxide and ammonia tend to deviate to a greater extent from the ideal behavior. Gases with higher molecular interactions have higher critical temperature. Best of luck for your exams. Do well.
That's about all we have time for today. But there's a lot more to check out on our website, www.topperlearning.com. The ideal way to be a topper is to keep practicing till you get it right. On that note, keep thinking and keep topping.